What if I told you that the reason you refresh your social media feed, the way a video game doles out rewards, and the pecking of a pigeon in a box from the 1950s are all connected by the same hidden rulebook? It sounds kind of wild, but today we're going to pull back the curtain on the secret architecture of our own behavior.
And it all starts right here, with this pigeon. This is a look inside the legendary Skinner box, named after the psychologist B.F. Skinner. See, he wasn't really just studying pigeons. He was asking a much bigger question. What are the fundamental rules that make us, and pretty much all animals, do the things we do?
So here's our game plan. We're going to start inside Skinner's original lab, then see how he literally made behavior visible. After that, we'll look at the incredible limits of that old-school approach, and then, this is the cool part, we'll jump to today to see how computer code is basically finishing the work he started.
Okay, so what was actually going on inside that little box? Well, it was brilliant, and brilliantly simple. The whole setup was really straightforward. On one side, you've got the pigeon. On the other side of that panel, you have all the machinery. The pigeon pecks a little key, and if the conditions are right, a food dispenser gives it a reward. That's it. Simple action, simple consequence. The real genius wasn't the box itself, but the rules that decided when a peck actually earned that reward. All right, so the next challenge was a big one. How do you even see the patterns that pop up from these rules? I mean, how do you take something as messy and fluid as behavior and get it down on paper? Well, the answer is in this idea, schedules of reinforcement. Now, that's just a formal name for the rule book. A rule could be something like reward every 10th peck, or maybe reward the very first peck after 1 minute passes. It's the exact same logic that keeps you pulling down to refresh your social feed, right? Hoping for that little dopamine hit of a new post that isn't always there. By just tweaking these rules, Skinner and his colleague Charles Furster found they could completely change the pigeon's behavior. And this is how they saw it all happening. Skinner himself said this device was his most important scientific contribution. It's called the cumulative recorder. The best way to think about it is like a seismograph, but instead of earthquakes, it's measuring actions. The paper moves along at a constant speed, and every single time the pigeon pecks that key, the pen just ticks up a notch. Now, looking at this slide, what's so cool is how you can learn to read it. This is a literal picture of behavior over time. If you see a steep slope, that means the pigeon is pecking super fast. A shallow slope? A much slower pace. And a totally flat line? Well, that means the pigeon's taking a break. All of a sudden, you can see the rhythm of behavior right there on the paper. And this right here illustrates their biggest, most groundbreaking discovery. These patterns weren't just a pigeon thing. No way. Didn't matter if it was a rat pressing a lever or a person pushing a button. The same rules, the same schedules, produced the exact same patterns of behavior. They had stumbled onto something universal. But, and this is a big but, uncovering these universal laws took a truly staggering amount of work, an effort that really pushed the boundaries of what was even possible in a physical lab. Get this, the data for their huge, foundational book, Schedules of Reinforcement, came from over 70,000 hours of recorded behavior. That's almost 8 years of non-stop observation. They even dedicated the book to the pigeon staff, which was their nickname for the graduate students who kept these experiments running 24/7. And in all those hours, they recorded roughly 250 million responses. 250 million! Every single peck meticulously tracked by these clunky mechanical relays and that little ink pen. It's just mind-boggling. But here's the fundamental problem they ran into. You can't just go up to a pigeon and say, hey, could you peck exactly 50 times a minute for me? And then 51? And then 52? It doesn't work that way. You can only set the rules and then watch what the pigeon chooses to do. And that left these huge, gaping holes in their data. It made it impossible to map out the entire landscape of behavior. So, how in the world do you solve a problem like that? Well, today, researchers have found a way, and it involves moving from the physical lab to the virtual one. Which brings us right to the critical question, how do you fill in those gaps? You can't test every single possibility with a real animal, but what if you could? What if you could find the single most optimal strategy for any given rule? You use a computer. The Animal Lab is absolutely fantastic for showing us how real, living organisms actually navigate the rules with all their biological quirks and limits. But a computer simulation? It can test every single possibility, from 1 peck an hour to hundreds a minute, to calculate the mathematically perfect or optimal way to behave. And that is exactly what modern tools are doing.
This comes from a recent paper describing an R script cleverly named Beak. It basically simulates a virtual pigeon, and that lets researchers explore what they call insurmountable possibilities, the exact response rates that Skinner's team could only dream of testing.
And this brings everything together, offering this powerful new lens for understanding our own actions.
The researchers came up with this really beautiful analogy. Think of the computer simulation as creating a perfect, flawless map of the territory. It shows every single peak of high reward and every valley of wasted effort. The animal experiment, then, shows us how a real traveler, whether it's a pigeon or a person, actually makes their journey through that territory. And the really interesting part is where the traveler's path is different from the perfect route on the map.
So, the simulations give us the normative rules. That's the perfect, most efficient way to do things, mathematically speaking. The experiments, on the other hand, show us effective behaviors, how living things actually get the job done in the messy real world. That gap, the space between the perfect path and the one we actually walk, that's where you find all the fascinating biases, shortcuts, and constraints that make us human.
So this all leaves us with a final thought to chew on. From the pull to refresh that doesn't always give you something new, to the unpredictable rewards in a game, these schedules are literally all around us, quietly shaping what we do all day long. The question is, can you see the map for the territory you're traveling in?